morning, everyone. We are Group 4 with members Sashi, Aradhya, Namrata, Bhavan, and myself. Today's topic for the presentation is Machine Learning Driven Network Security, Behavior Analysis for IoT DDoS Attack Detection. In recent years, IoT networks have evolved how we interact with technology. These networks have enabled easy device connectivity, cloud access, and efficient resource utilization. However, there is always a risk that comes with this technological advancement, particularly in the form of distributed denial of service attacks, which send a huge amount of internet traffic to flood IoT networks. What motivated us to choose this project are number one, IoT expansion and vulnerability, which requires robust security against evolving DDoS threats. Secondly, the traditional measures fall short, requiring adaptive machine learning for dynamic threat detection. Lastly, considering that sensitive data is at stake, machine learning can ensure data integrity and user trust. Here is the objective of our project. We aim to design a hybrid algorithm that combines several machine learning techniques like k-nearest neighbor, random forest, and support vector machine to train a model that can be used to detect and classify the type of DDoS attack with greater accuracy. These are a few of our project references. We have referred to IEEE papers to understand the data sets, methods, model used, and implementation, and to gain insights for our project. So like you see here, we are following a CRISP-TM methodology for this project, where we have split the entire project into 7 different phases. The first step is business understanding, where one understands the project requirements, focuses on IoT source data and the related problem statement. The second step is data understanding, where we collect data sets for IoT DDoS attack and conduct the exploratory data analysis on the same. The third step is data preparation, where we undergo data cleansing, data transformation, and finally split the data into 80% train and test by 20%. We'll be discussing each step in detail after a few following slides. The fourth step is modeling, where we develop several models for this project, implement ensemble techniques on the developed models, and evaluate the performance based on certain evaluation metrics. And last is the deployment phase, where we deploy our project in the Streamlight application for users' access and visibility. Coming to the data source, the data is sourced from the approximate IoT 23 data set. It was first published in the year 2020. And this last data set provides real and labeled IoT malware and benign traffic, which will help us to develop machine learning algorithms.
Moving on to data collection, we encountered different kinds of file formats. One of them is the .pcap file, which had the network traffic captures original data set. And the label file consists of data sets with labels corresponding to those network traffic captures. To give a brief about the data set, it consists of 20 malware captures and 3 benign captures corresponding to the IoT devices. It also consists of different kinds of labels like CNC, DDoS, and many more, but our primary goal is to just focus on identifying DDoS. This is our project architecture. We used Google Colab to retrieve the data, to perform exploratory data analysis, pre-process the data, and data preparation. And then as part of data preparation, we split the data into trained data set and test data set, which was then used for modeling. For modeling, we built individual models like random forest, SVM, and KNN, which was also used to implement ensemble techniques containing the algorithms RF and SVM, RF and KNN, SVM and KNN. Finally, we deployed the project using AWS to make it available for the users. This is our data process flow. The first step is to source the IoT data containing CSV format. The next step is conducting exploratory data analysis, where we did null checks, statistical distribution, and checked for correlations. The third step is data cleansing, where we dropped unwanted columns, renamed the columns, handled missing values, and duplicate records. The fourth part is data transformation, where we did label encoding, standardized the numerical features, and we binned the different attacks. The final step was data preparation, where we split the data set into 80% training and 20% test.
So this is our IoT data set. You can see the link, the API is mentioned. We conducted exploratory data analysis for the data obtained. So we can see that there are 21 available columns. So out of the available columns, most of the data types are either object or float, which gives an insight that the data types of the columns has to be changed. Suppose there are date columns that has to be changed to date time, and some of the float columns can be changed to integer so that memory utilization can be executed. So these are the, we saw that if there are any null values in the columns, and as seen, there are pretty less number of null values present, although one or two values, we'll have to eliminate it or handle the null values. So this is the correlation matrix, which tells how each attribute are correlated with each other. So we can see that OB count and RP count displays the highest correlation in the data set, whereas OP count and H address, it displays the least correlation. The correlation scale is given in the right side. So this is the pair plot visualization, which tells how each, if there are any underlying patterns between the attributes and how each value is gets influenced by the value of another attribute. So as seen in the bar plot, the population of data values for non-DDoS is highly, it's really more than compared to malicious DDoS, which tells us that the model can't be trained with this data, because given the data, if the model is being trained, then it'll be partially tilted towards the non-DDoS values, and there'll be improper analysis. So we'll need to balance the data values. And this is the box plot seen, where the mean, mode, and the potential outliers are visible through all the numerical attributes. And through the statistical distribution, we can improve the quality of data.
Yeah, so once the data EDA is performed on the data set, we go on to cleanse the data set in terms of handling the null values, in terms of replacing the dashes with the null values, in terms of reducing this space taken by the data set. So as you can see here, there are a few null values which are technically handled by KN and imputation, where we perform the mean imputation in terms of handling these null values, and we go on to rename the columns in terms of human interpretable format. And also we drop the unwanted columns as well, in terms of trying to save the space taken by the data set. So the figure above shows how the data looked like before data cleansing, and the figure after shows the data set after data cleansing. So once the data cleansing is done, the data set is transformed into a format that can be interpreted by the machine learning algorithms. The sample figure in the top shows the data before performing any sort of transformations. So also one requirement for machine learning algorithms are all the column values should be numerical format. And we can see here there's a column called missed byte count, which is not in a numerical format. So hence we go on to perform a label encoding in terms of transforming that into numerical format. Also, there were a few null values as well that we go on to handle using mean imputation. And here we can see the figure below shows the data after label encoding, where the missed byte count is in numerical format. And once we handle all the null values and perform the label encoding, we go on to perform data standardization in terms of basically standardizing numerical columns for consistency. So this basically facilitates model training on a common scale. So here we can see the first figure is before standardization, and second figure is after data standardization. So once that's done, we can also see there's a column called category, where this essentially shows what kind of attack is performed on that IoT device. And since here the project scope is only DDoS and non-DDoS attacks, so we go on to perform binning in terms of just splitting these values into DDoS and non-DDoS category, as you can see in figure 2, which is in the bottom. And after that, we go on to perform regularization in terms of ensuring that the model doesn't overfit, and we perform the L1 regularization for that. And here you can see the graph which shows the coefficients, the contribution of the prediction. And so once that's done, we go on to perform so after that, we go on to perform oversampling to essentially increase the number of records which is present in the malicious DDoS category. And here in this bar graph, we can clearly see that the number of non-DDoS and DDoS attacks are the same, which we go on to use for machine learning model training.
In the modeling, we'll be using 3 algorithms, basically random forest, KNN, and support vector machine. These are separately individually implemented to check their accuracies and their performance before proceeding on to the ensemble techniques. In the ensemble techniques, we have chosen to work with voting classifier. Voting classifier is a type of ensemble learning technique which helps improve overall model performance by combining predictions from multiple base models. As you know, we have already chosen to work with random forest, KNN, and KNN. The voting classifier has an accuracy of 0.98, and with KNN and SVM, it has an accuracy of 82. And with random forest and SVM, we have secured an accuracy of 1. The reason to choose the ensemble technique as a voting classifier is due to its ability to reduce the overfitting and handling of model uncertainty, and its simple implementation along with handling imbalanced data, which are key factors which were discussed earlier. Now we move on to the model deployment. In the model deployment for the front end, we have used the Streamlit, and for the version control system, we have used Git, and for the IDE, we have used a Spider from Anaconda, and for the database of storage, we have used S3. We have replaced the API with the version control system and the IDE to check out how this application works. By clicking on that, we are redirected to our URL, which is a front end of the application. Now we have just need to drop the file which contains the test data. So by clicking on the test data, we have secured this CSV file, and we just press on the predict network intrusion, and we will be obtaining about the DDoS and non-DDoS attack in few minutes. Yeah, this is a prediction results that there are 2,482 records of malicious DDoS attacks from all the data we have collected. So now moving on to the conclusion part. ML models, RFKNN, and SVM enhance IoT security against DDoS, and usage of ensemble techniques can provide robustness, stability, and reduced risk of model bias. And preventive approaches strengthens IoT security against DDoS crimes. Future scope includes exploring more futures and strategies for IoT behavior analysis, and also the concept of mitigation. Mitigation of DDoS is a crucial step, and evaluating robustness under varying networks and new IoT devices is also future scope. So, thank you.